Let's study a paper that is, honestly, the beating heart of your Floquet toolbox. Nixon, Unal, and Schneider. Individually tunable tunneling coefficients in optical lattices using local periodic driving. Out of the Cavendish Lab in Cambridge, Archive 2309.12124, published in Quantum Science and Technology in 2024. George, I want the mathematics tonight, not the vibes. The actual mechanism by which you shake a lattice site and a tunneling amplitude bends to your will.
Good, because this paper rewards that. It's a theory proposal, but it's a beautifully mechanical one. The whole thing is really a single idea pushed relentlessly. If you wiggle the energy of individual lattice sites in time, periodically, then in the time-averaged effective description, the tunneling between sites gets multiplied by a Bessel function. And once you have that dial, a Bessel function you control site by site, you can build almost any one-dimensional hopping model you want, and a startling amount of two-dimensional physics too, including magnetic flux.
And for our project, the Cold Atom Black Hole Simulator, this is Pillar B. This is the toolbox that lets us later carve a horizon into the lattice. Our sims R01, R02, R03 are literally reproductions of the figures in this paper, so I want to earn every one of them tonight.
Then let's earn them. Let me set the stage with the Hamiltonian, because everything descends from it. We're doing non-interacting particles in a tight binding lattice. The total Hamiltonian is time-dependent. H of t equals h0 plus v of t.
Break those two pieces apart for me.
H0 is the static lattice. It's minus j times the sum over nearest neighbor pairs, written angle bracket I, j angle bracket, of a dagger IAJ. So j is the bare tunneling amplitude, the rate at which a particle hops from site j to site I. The A dagger I is the creation operator on site I, AJ is the annihilation operator on site j. So A dagger I AJ means destroy a particle on j, create it on I. That's a hop, and the minus sign in front of j is just the standard tight binding convention.
Standard so far, that's just atoms sitting in an optical lattice hopping around at rate j.
Exactly. Now the second piece, v of t, is where the magic enters. V of t equals the sum over sites j of wj of t times nj. Here nj is the number operator on site j, it just counts how many particles are on that site. And wj of t is a time-periodic on-site energy. Periodic meaning wj of t equals wj of t plus t, where t is the drive period and the frequency omega equals 2 pi over t.
So physically, wj of t is me shining a laser on site j and jiggling its energy up and down in time.
Precisely. In the experiment, you focus an off-resonant laser, think of an optical tweezer beam, onto an individual site, and you modulate its intensity. That raises and lowers the potential energy of an atom sitting there. Crucially, you can do this site by site. Different wj for different sites. That locality is the entire point of the paper. Traditional optical lattice Floquet driving shakes the whole lattice globally. Here, we address individual sites.
Okay, so we have a Hamiltonian that's periodic in time. That word periodic is a flag. It means Floquet theory applies. Walk me into it. But first, there's a gauge transformation you do before you even start, right? Into what they call the lattice frame.
And it's worth understanding why. Because it's a recurring trick. The on-site drive wj of t sits on the diagonal of the Hamiltonian. It's a potential energy term. That's awkward. What you'd rather have is the drive expressed as a modulation of the hopping itself. So you do a gauge transformation, a unitary rotation into a co-moving frame, that removes the on-site potentials and instead dresses each hopping term with a time-dependent phase. That phase is called a Peierls phase.
Peierls, as in the substitution that puts a magnetic vector potential into a lattice.
The very same. Rudolf Peierls, 1933. In the lattice frame, the Hamiltonian becomes tilde h of θ equals minus j, sum over nearest neighbors, of e to the I phi ij of t times a dagger iaj. So instead of a bare hop, every hop from j to I now carries a complex phase factor, e to the I phi ij of t.
And what is phi ij of t concretely?
This is the key formula, so let me say it carefully. Phi ij of Ta equals the integral from t0 to t of the quantity in brackets, wj of tau minus wi of tau, d tau, plus a constant phi naught ij. In words, the Piles phase on the link from j to I is the time integral of the difference in the drives on the two sites. The difference, wj minus wi.
Stop, that difference is doing enormous work. It means if I drive both sites identically, Wi equals Wj, the difference is zero, the phase is zero, and I get back the bare tunnelling. Nothing happens.
Nothing happens exactly, and that is the deepest single sentence in the setup. The engineered Piles phase of a link depends solely on the relative modulation between its two endpoints. Common mode driving is invisible. Only the differential drive matters. Every result downstream, the Bessel renormalization, the SSH model, the synthetic flux, is a consequence of controlling that difference.
There's also a constant phi naught ij. What's that for?
A gauge choice, a bookkeeping convenience. They pick it so that the Piles phase has zero time average. The integral of phi ij of t over one full period is zero. That centers the phase around zero and makes the later expansions cleaner. And note they've set h bar equals 1 from here on, so energy and frequency have the same units, and time is inverse energy.
Good. Now, Floquet, we've got tilde h of t, periodic in time. How do we define energy when energy isn't even conserved?
Right, that's the conceptual hurdle. When the Hamiltonian depends on time, energy is not a good quantum number. But because it's periodic, something else is conserved, quasi-energy. The object you study is the time evolution operator over one period. Write tilde u of t, t0 equals the time-ordered exponential of minus I, integral from t0 to t, of tilde h of tau d tau. The script t out front denotes time ordering, because the Hamiltonian at different times doesn't commute with itself, so you can't just exponentiate the integral naively.
Time ordering. The operators have to be stacked in chronological order as you build up the evolution.
Yes. Now here's the Floquet move. Propagate over exactly one period, from t0 to t0 plus t. You get an operator, tilde u of t0 plus t, t0. Its eigenvalues are pure phases, it's unitary, and you write each eigenvalue as e to the minus I epsilon t. That epsilon is the quasi-energy. It plays the role energy would play, but it's only defined modulo omega, because adding a full 2 pi to the phase changes nothing.
Modulo omega. That's the Floquet analogue of crystal momentum living in a Brillouin zone. Quasi-energy lives in a quasi-energy zone.
A perfect analogy and not a coincidence. It's the same mathematics, periodicity in time instead of space. Now, from that one-period operator, you define an effective, time-independent Hamiltonian. Because if you look at the system only at stroboscopic instants, once per period, t0, t0 plus t, t0 plus 2t, and so on, the evolution looks like it's generated by a constant Hamiltonian. Formally, tilde u of t0 plus nt, t0 equals e to the minus inths, where hs is the stroboscopic Hamiltonian, and n is an integer number of periods.
So the stroboscopic Hamiltonian is the effective static Hamiltonian you'd infer if you only ever photographed the system once per drive cycle.
That's it. But there's a subtlety the paper is careful about, and it matters for our simulations. The stroboscopic Hamiltonian depends on t0, on which phase of the drive cycle you choose to start your stopwatch. There's a whole family of them, hs parameterized by t0 in the interval 0 to t. They're all related by unitary transformations, so they share a spectrum, but they're different operators.
That t0 dependence sounds like a nuisance. Is it physical?
It's the freedom of when you look, and it's tied to the micromotion, the fast wiggle of the wave function within a single period. They define a micromotion operator, p of t, t0, which is tilde u of t, t0 times e to the plus ihs times t minus t0. It describes the evolution in between the stroboscopic snapshots, and it has the lovely property that over a full period it reduces to the identity. P of T naught plus T comma T naught equals 1. The micromotion returns to itself every period.
So the full evolution factorizes. A slow effective part governed by a static Hamiltonian, dressed by a fast periodic breathing that closes up each cycle.
Beautifully put. And because the T naught dependence is a nuisance for analytics, they introduce one more object, the effective Hamiltonian, HF, which is explicitly T naught independent. It's related to the stroboscopic one by a unitary HS equals Q of T naught, HF, Q dagger of T naught. The effective Hamiltonian is the Floquet gauge invariant description, the clean gauge-free thing you quote in a paper. The stroboscopic one is what you compute numerically to check.
And that split is exactly our numerical strategy in the sims, isn't it? We compute the effective Hamiltonian analytically from the high-frequency expansion, and we compute the stroboscopic Hamiltonian by brute force integrating the Schrödinger equation, and we check they agree.
That's exactly the workflow, and it's Appendix B of the paper. Numerically, you evolve for one period, diagonalize the one-period operator, U of T naught plus T comma T naught acting on PSIN gives eigenvalue UN. And then the quasi-energy is epsilon n equals I over T times the natural log of UN. Reassemble HS as the sum over n of epsilon n. Outer product PSIN with PSIN. That's the numerically exact stroboscopic Hamiltonian, no truncation, all orders of the drive included.
Okay, so we have the exact but numerical object, and we want an analytic handle. That's the high-frequency expansion. Take me through it.
The idea is to expand the effective Hamiltonian in inverse powers of the drive frequency. When omega is large, the drive is fast compared to the tunneling. The corrections are small. Formally, HF equals the sum from n equals 0 to infinity of 1 over omega to the n times HF super n. The leading term HF super 0 is the 0th order. The next, HF super 1, is the 1 over omega correction, and so on.
Give me the two leading terms explicitly.
The 0th order term is simply the time average of the lattice frame Hamiltonian. HF super 0 equals tilde H naught, where tilde H naught is the 0th Fourier component, the average over one period of tilde H of t. The first order term is HF super 1 equals the sum, from m equals 1 to infinity, of 1 over m, times the commutator of tilde hm with tilde h minus m.
Unpack those Fourier components.
Tilde hm is defined as 1 over t, integral from 0 to t, of e to the minus im omega t times tilde h of t dt. It's the mth Fourier harmonic of the time periodic Hamiltonian. U Fourier decompose the driven Hamiltonian in time, and tilde hm is the weight of the e to the im omega t component. So the 0th harmonic tilde h naught is the dc part, the time average, and the higher harmonics capture the wiggle.
And the first order correction is built from commutators of the plus m and minus m harmonics. The commutator matters because if those harmonics commuted, the correction would vanish.
Hold that thought, because it becomes the punchline for why one dimension is so clean. Let's now actually drive something. Section 3, Part A. Drive a single site.
The simplest possible experiment. One site, call it B, gets a cosine drive.
V of t equals a cosine omega t times nb. Amplitude A, frequency omega, acting only on the number operator of site B. Everything else is bare. Now go to the lattice frame and compute the pile's phase. For a link touching site B, the drive difference is a cosine omega tau on one endpoint and 0 on the other. Integrate that in time, and you get a phase proportional to sine omega t. Specifically, the phase oscillates as a over omega times sine omega t.
The hopping to and from B picks up a factor e to the I times a over omega times sine omega t.
Right. Now take the time average, the 0th order effective Hamiltonian. You need the time average of e to the ix sine omega t, and there is a classical identity for exactly that. The time average of e to the iz sine theta over a full cycle is the Bessel function of the first kind, order 0 of z. J naught of z. This is the Jacobi-Anger expansion evaluated at its DC component.
There it is. The Bessel function falls out of a time average of a complex exponential of a sine, say the punchline.
The effective Hamiltonian is HF super 0 equals minus j, sum over neighbors, epsilon ij, a dagger I aj. And the renormalization factor epsilon ij equals j naught of a over omega, if the link touches the driven site B and equals 1 otherwise. So the bare tunneling j becomes an effective tunneling j prime equals j times j naught of a over omega, but only on the two bonds flanking the driven site.
Let me make sure I have the geometry. Site B sits in a chain. It has a neighbour on the left and a neighbour on the right. Two bonds. Both of those bonds get multiplied by j naught of a over omega. Every other bond in the chain is untouched.
Exactly two bonds, the ones adjacent to B. This is figure 1 and figure 2 of the paper, and it's your simulation R01. Now let's actually feel this Bessel function, because it is the single most important curve in the whole toolbox.
Please, what does j naught of a over omega do as I crank the drive?
Define the dimensionless drive strength as x equals a over omega, amplitude over frequency. At x equals 0, no drive, j naught of 0 equals 1, bare tunneling, untouched. As you increase x, j naught of x decreases smoothly, monotonically at first, so the tunneling weakens. You're dynamically suppressing hopping just by shaking the site.
This is dynamical localization, the old Dunlap-Kenckrey result, atoms frozen by shaking.
The same physics, now local. Keep increasing x, and j naught reaches its first zero at x equals 2.405. 2.405 roughly. At that magic value, the effective tunneling is exactly 0. The bond is severed. The atom cannot hop across that link at all, even though the bare lattice barrier hasn't changed one bit.
2.405. That number should be tattooed somewhere in our codebase. That's how we cut a bond cleanly.
It's the first zero of j naught, and yes, it's the scalpel. Push further, past 2.405, and j naught goes negative. The effective tunneling changes sign, so now you have not just weakening and severing, but sign reversal of the hopping amplitude, and then it comes back up, crosses 0 again near 5.52, goes positive, and oscillates with ever-decreasing amplitude as x grows.
So a single knob, the ratio A over omega, sweeps the bond continuously from full strength, down through 0, into negative, and back. That's the whole Swiss Army knife.
That's the whole knife, and figure 2C of the paper is precisely this. They plot the renormalized nearest neighbor tunneling J prime over J, extracted from the numerically exact stroboscopic Hamiltonian, as red dots against the analytic gray curve J naught of A over omega. They lie right on top of each other. That agreement is your R01 validation target.
Now I have to ask the awkward question a referee would ask. The stroboscopic Hamiltonian is exact. The Bessel result is only 0th order. Where did the higher orders go? Why does 0th order work so well?
This is genuinely elegant, and it's Appendix A. Remember, the first order correction is a sum of commutators tilde hm with tilde h minus m. In these on-site cosine-driven one-dimensional models, that first-order term vanishes identically. Not is small, vanishes. So the leading correction to the Bessel result is not order 1 over omega, it's order 1 over omega squared.
Show me why it vanishes. I don't want to take it on faith.
Let's walk it. The Fourier harmonics in the lattice frame are tilde hm equals minus j, sum over neighbors, a dagger I aj, times jm of the quantity ai minus aj over omega, where now jm is the Bessel function of order m, and ai, aj are the drive amplitudes on the two sites. That comes from Fourier expanding the exponential of a sin using the full Jacobi-Anger series. E to the iz sine omega t equals the sum over m of jm of z times e to the im omega t. Each harmonic gets a Bessel of order m.
So the mth harmonic of the hopping is weighted by the mth Bessel function of the relative drive. Good.
Now the commutator tilde ham with tilde h minus m. First, use the identity j minus m of x equals minus 1 to the m times jm of x. The Bessel functions of negative order are just the positive order ones up to a sign, so tilde h minus m is proportional to the same hopping structure with a sign. When you expand the commutator of two hopping operators, a sum of a dagger are terms with another sum of a dagger are terms, you get products where the annihilation index of one matches the creation index of the other. You get terms that would represent next nearest neighbor hops from site j to site j plus 2 and on-site terms.
And they cancel.
They cancel in pairs. For every next nearest neighbor term generated going one way around, there's an equal and opposite one going the other way, because the Bessel coefficients that multiply them are symmetric. Jm of aj minus aj plus 1 appears with both signs. Line by line in the appendix, the a dagger j aj plus 2 terms cancel against a dagger j plus 2 aj terms, and the on-site number terms cancel among themselves. The total commutator is 0.
So the physical statement is, in one dimension, with pure on-site cosine driving, the first-order Floquet correction is exactly absent, and your effective Hamiltonian is the Bessel result up to tiny 1 over omega squared crumbs.
Which is why in figure 2b, when they plot the stroboscopic Hamiltonian on a logarithmic color scale, you can just barely see faint longer-range hoppings appearing. Those are the 1 over omega squared effects. On a linear scale, they're invisible. In practice, choose omega a few tens of j, and they're utterly negligible.
This is a good moment to pause and connect it to us. Every bond in our black hole lattice is going to be one of these Bessel renormalized bonds. When we build a horizon, we're spatially varying A over omega site by site, so the effective hopping traces out the metric we want. So the fidelity of that whole construction rests on this 1 over omega squared smallness.
Rests on exactly that, and it's why the paper hammers the point. The cleaner the separation of scales, omega much larger than j, the more faithfully your engineered Hamiltonian is the Bessel-dressed tight-binding model and nothing else. When we later encode a curved space-time or a horizon, we are trusting that the atoms feel HF super zero and that the corrections are controlled. This paper is the license to trust it.
Let's keep building. Driving one site renormalizes two bonds, but sometimes I want to change exactly one bond. How?
Section 3b, and it's a cute trick from an earlier Wang-Unal-Eckart proposal. Instead of driving one site, you drive every site on one side of the target link, all with the same function. So v of t equals a cosine omega t times the sum over all sites j greater than b of nj. Every site from b plus 1 onward is driven identically.
And now the difference argument kicks in. Inside that driven block, neighbouring sites have identical drives, so their relative modulation is 0. Those bonds are untouched. The only place there's a mismatch is at the boundary of the block.
You've got it entirely. The only link where the drive difference is non-zero is between site B, which is undriven, and site B plus 1, which is driven. So the renormalization factor, epsilon ij, equals j naught of a over omega if the pair ij is exactly b and b plus 1, and 1 everywhere else. One single bond bent by a Bessel function. That's figure 3.
Which feels almost paradoxical. You drove half the lattice to modify one bond, but it works because only the seam matters.
The seam. It's the same lesson as before, wearing a different hat. Relative drive, not absolute drive. Now the crown jewel of the one-dimensional story is section 3c, full programmability. Drive every site, same frequency, but with individually chosen amplitudes.
Different amplitude on every site, so AJ is now a whole list of numbers, one per site.
Right. V of TA equals cosine omega t times the sum over j of aj nj. Same frequency omega everywhere, but the amplitude aj is site-specific. Go to the lattice frame, and the hopping from j to I now carries the phase e to the I, times the quantity ai minus aj over omega, times sine omega t.
The relative amplitude AI minus AJ sets the phase amplitude on that bond.
And so, taking the time average, the 0th order effective Hamiltonian is tilde h f super 0 equals minus j, sum over neighbors, A dagger I AJ times J naught of the absolute value of AI minus AJ over omega. Each bond, independently, is multiplied by a Bessel function whose argument is the magnitude of the amplitude difference across that bond, divided by omega.
So this is the master formula for one dimension. Every bond's effective strength equals J times J naught of the magnitude of the amplitude difference across it over omega. Choose the list of amplitudes and you choose the entire hopping profile of the chain.
That is the master formula, and everything else in one dimension is an application of it. And note the absolute value, because J naught is an even function. J naught of minus x equals J naught of x. Only the magnitude of the difference matters for the effective magnitude. And again, the first-order correction vanishes because the plus m and minus m Fourier components commute here too, for the same reason as before. Zeroth order 1 over omega squared corrections. Clean.
Right, let's cash it in. The SSH model, this is our RO2. Walk me through building Su-Schrieffer-Heeger from this.
The SSH model, Su-Schrieffer-Heeger, 1979, originally for polyacetylene, is a one-dimensional chain with alternating strong and weak bonds. Bond, weak bond, strong bond, weak bond, and so on. It's the canonical topological insulator in one dimension. Depending on where you cut the chain, you either have or don't have a protected zero-energy state living on the edge.
And we want to make the bonds alternate using only on-site driving. So I need a drive pattern that makes the amplitude difference across bonds alternate between two values.
Right. They use a four-site periodic sequence of amplitudes with two magnitudes, C1 and C2, and a sign flip. Concretely, AJ equals C1 if J is 0 mod 4, C2 if J is 1 mod 4, minus C1 if J is 2 mod 4, minus C2 if J is 3 mod 4. So going down the chain, the amplitudes read C1, C2, minus C1, minus C2, and repeat.
Why the sign flips? Why not just C1, C2, C1, C2?
Because of the different structure. Let's compute the magnitude of AJ minus AJ plus 1. Take the first bond from the C1 site to the C2 site. The difference is C1 minus C2. Now the next bond from the C2 site to the minus C1 site. The difference is C2 minus C1, which is C2 plus C1. So the magnitudes alternate between the magnitude of C1 minus C2 and the magnitude of C1 plus C2.
The sign flip is what turns the second bond's difference into a sum. Without it, every bond would have the same difference and you'd get a uniform chain, not an alternating one.
Exactly right. The minus signs are the trick that makes even bonds see C1 minus C2 and odd bonds see C1 plus C2. So the effective tunnelings alternate. J prime equals J times J naught of the magnitude of C1 minus C2 over omega, and J double prime equals J times J naught of the magnitude of C1 plus C2 over omega. Two distinct bond strengths alternating down the chain. That is the SSH model.
And physically, the sign flip every second site is a pi phase shift in the drive. You invert the cosine.
A pi phase shift, yes, cosine of omega t plus pi is minus cosine omega t. So experimentally, you need two drive faces, in phase and out of phase, which is very doable. They also mention an alternative all-in-phase sequence, C1, then C1 plus C2, then C2, then 0. That produces the same SSH model without needing the pi phase, at the cost of larger amplitudes. Nice for the lab.
Now the payoff, the edge state. Figure 5, what do we actually see?
They build the numerically exact stroboscopic Hamiltonian for a short chain with, in their example, C1 equals 29, C2 equals 13, omega equals 25, all in units of J. Figure 5a shows the matrix. The off-diagonal elements are the hoppings, and you can literally see them alternate between two values, with alternating signs. Then figure 5b, they find the zero-energy eigenstate and plot its probability density. It is exponentially localized at one edge of the chain and decays into the bulk.
That's the topological edge mode, and it's protected by what exactly in this language?
By the Zach phase, the one-dimensional Berry phase across the Brillouin zone. When the intracell bond is weaker than the intercell bond, the Zach phase is pi. The topology is non-trivial, and a zero-energy boundary mode is guaranteed. When the ratio is the other way, ZAC phase 0, trivial, no edge mode. The SSH chain sits right at the boundary of that classification, which is why it's the teaching example. And here we've conjured it entirely out of shaking on-site energies. No custom lattice, no exotic wavelengths.
Which is the selling point. You'd normally need a special superlattice laser to dimerize the chain. Here it's just a drive pattern.
And it generalizes trivially, which the special lasers do not. Section 3E, extended SSH, the SSH3 and SSH4 models. These have 3 or 4 distinct bond values cycling, which gives access to higher winding numbers, richer topology, more edge modes.
How does the recipe extend?
Same logic, longer sequence. For SSH3, you use 3 amplitudes, C1, C2, C3 and a 6-site pattern, C1, C2, C3, minus C1, minus C2, minus C3, repeating. Work out the neighbor differences and you get 3 distinct bond magnitudes cycling. Magnitude of C1 minus C2, magnitude of C2 minus C3, and magnitude of C1 plus C3. The general rule they state is lovely. To get a pattern with a given number of distinct effective tunnelings, you use a spatial drive period that is double that number.
Double, because of the sign flip trick, you need the mirror image negative block to turn some differences into sums.
Precisely the reason. SSH4 then needs a period 8 sequence, C1 through C4, then minus C1 through minus C4. Figure 6 shows both SSH3 and SSH4 verified against the stroboscopic Hamiltonian. And this is where the paper first winks at us. They explicitly say this full local control lets you study strained one-dimensional materials, where strain varies spatially, or to encode curved spacetimes to investigate the quantum dynamics around black holes, citing the companion paper. That companion is Benhimo, Nixon, Dager, Schneider, Pachos.
That companion paper is the other half of our project, the black hole side. So this is the explicit handshake between Pillar B, the toolbox, and the physics we actually want. The horizon is encoded as a spatial profile of these Bessel renormalized bonds.
That's the through line. A black hole horizon in the analog gravity dictionary is where the effective speed of light on the lattice, set by the local hopping, goes to 0 or where the metric turns over. And the local hopping is exactly the knob this paper hands you, J times J0 of the local drive strength. You paint the metric by painting the amplitudes AJ.
Let me raise something before we go to 2 dimensions, because it confused me on first read. In 1 dimension, they keep saying the sign, or even a complex phase, of the tunneling doesn't matter. But then in 2 dimensions, it suddenly matters enormously. Reconcile that.
This is a genuinely important gauge subtlety, and they handle it carefully. In a one-dimensional chain with only nearest neighbor hopping, a negative or complex tunneling amplitude is physically indistinguishable from a positive one of the same magnitude. Why? Because you can absorb the phase into the definition of the Wannier functions. Redefine the phase of the orbital on each site, a local gauge transformation, and you can rotate away any bond phase. There are no closed loops, so there's nothing to trap the phase.
No closed loops, that's the operative phrase. In a line, you can always gauge the phases away because you can walk down the chain, reassigning phases one site at a time with no consistency conflict.
Exactly. But the moment you have a closed loop, a plaquette in 2 dimensions, or long-range hoppings that close a loop, or a synthetic extra dimension, you cannot gauge away the phases freely. The sum of the phases around a closed loop is gauge invariant. That loop sum is a flux, and a Aharonov-Bohm flux, a magnetic flux through the plaquette. It's physical. It cannot be removed by any redefinition of local phases.
So in 1 dimension, the phase is a free gauge choice. Around a loop, the total phase is a physical magnetic flux. That's the bridge to the 2-dimensional half of the paper.
That's the bridge. And they footnote a subtlety worth knowing. Even in 1 dimension, if you do a time-of-flight measurement, you leave the tight-binding description and can actually detect the difference between canonical and mechanical momentum. So the phase isn't metaphysically meaningless, it's just invisible to the tight-binding energetics. But for building Hamiltonians, in one dimension, only magnitudes matter. In 2 dimensions, loop phases become flux and matter enormously.
Let's go to 2 dimensions. First stop, the Lieb lattice. Why that geometry?
The Lieb lattice is a decorated square lattice. It's the geometry of the copper-oxygen planes in cuprate superconductors. Incidentally, it has 3 sites per unit cell. One family, call them the A sites, sit on the corners and form a simple square lattice. The other 2 families, B and C, sit on the edges, one on each edge between neighboring A sites. So every A to A connection actually goes through an intermediate B or C site.
So the A sites don't hop directly to each other. They hop via the edge sites.
Right? And that's the feature they exploit. If you drive the edge sites, the B and C sites, with local amplitudes AJ, then by the single site result, each such site's flanking bonds get renormalized by J0 of AJ over omega. And because every effective A to A link runs through exactly one driven edge site, you get individual control over every link of the emergent square lattice of A sites.
So you build a fully programmable square lattice, where every horizontal and vertical bond is independently tunable by driving the intermediate sites.
Independently tunable, yes. The effective Hamiltonian is minus J, sum over the driven edge sites and their neighbors, epsilon J, times the hop A dagger I AJ plus its conjugate, with epsilon J equals J0 of AJ over omega. One factor per edge site. Figure 7 shows it. Drive site 7 with amplitude 72 and omega 40, and the 2 bonds through it get renormalized by J0, which they compute to be about 0.34.
And they use the Bessel zero to cut connectivity.
That's the striking bit, figure 7c. They drive another edge site, site 10, with amplitude 96, so that J0 of 86 over 40 is essentially 0, sitting on the Bessel zero. And that turns off the link between sites 9 and 11 entirely. So you can carve holes and channels in the connectivity graph of a 2-dimensional lattice at will. They point out you can engineer dimensional crossovers, 1-dimensional to 2-dimensional, or bespoke graphs for quantum walks and even quantum annealing.
A programmable graph drawn with Bessel zeros. But, and here's the limitation, everything so far is real and positive. No flux yet. Where does flux come from?
That's section 4b, and it's the mathematical heart of the 2-dimensional story. Full control of a triangular plaquette, including the flux threading it. This is your RO3, and the new ingredient is 2-frequency driving.
Why a triangle and why 2 frequencies?
A triangle is the minimal closed loop, 3 sites, 3 bonds, 1 plaquette. It's the simplest place a gauge invariant flux can live, and the goal is ambitious. Control both the 3 relative tunneling magnitudes and the flux through the triangle, all independently. To break time reversal symmetry and make a bond genuinely complex, not gaugeable away, you need more than a single global frequency. So they drive 2 of the 3 sites, and they let those 2 sites be driven at different but commensurate frequencies with a relative phase.
Lay out the Hamiltonian for the triangle.
Label the sites 1, 2, 3. Sites 2 and 3 are driven. Site 1 is passive. The Hamiltonian is h of t equals minus j, sum over the 3 bonds of a dagger I aj, plus a2 cosine of alpha omega naught t, times n2 plus a3 cosine of beta omega naught t plus phi times n3. So site 2 is driven at frequency alpha times omega naught. Amplitude a2, site 3 at frequency beta times omega naught. Amplitude a3 with a relative phase phi. Omega naught is a base frequency, and alpha and beta are integers, so the 2 drives share a common period. T equals 2 pi over omega naught.
Commensurate frequencies, integer multiples of a base, so the whole thing is still periodic and Floquet still applies.
Essential, yes. If alpha over beta were irrational, there'd be no common period and no Floquet Hamiltonian. Now apply the high-frequency expansion. The 0th order effective Hamiltonian is minus J12, a dagger 1 a 2, minus J23, a dagger 2 a 3, minus J31, a dagger 3 a1, plus Hermitian conjugate, 3 renormalized bonds around the triangle.
And what are those 3 renormalized J's?
2 of them are ordinary Bessel functions. J12, the bond between the passive site 1 and the driven site 2 equals J times J naught of A2 over alpha omega naught. J31 between driven site 3 and passive site 1 equals J times J naught of A3 over beta omega naught. Standard single site renormalization, because each of those bonds touches exactly one driven site.
So each of those two bonds only sees one drive and reduces to the familiar J naught. It's the third bond, connecting the two driven sites, that's special.
That's the interesting one. J23, the bond between the two driven sites. It sees the difference of two different drives at two different frequencies with a relative phase. Its renormalization is a generalized two-variable, one-parameter Bessel function. Explicitly, J23 equals J times 1 over t, integral from minus t over 2 to plus t over 2, of e to the I times the quantity, A3 over beta omega naught times sine of beta omega naught t plus phi minus A2 over alpha omega naught times sine of alpha omega naught t, all dt.
So it's the time average of e to the I times the difference of the two integrated drives. Because the two drives have different frequencies and a phase offset, that average is not a simple J naught, it's a generalized Bessel function, and critically it can come out complex.
Complex, that's the whole game. When the integrand's imaginary part survives the time average, J23 acquires a phase. And the flux through the triangle is the argument, the phase angle, of the product of all three bond amplitudes. Capital phi equals the argument of J12 times J23 times J31. Since J12 and J31 are real in this gauge, the flux is essentially the phase of J23.
Now, when is J23 actually complex? Because if it's real, there's no flux, and we've done all this for nothing. What are the conditions?
This is Appendix C, and it's a clean symmetry argument. Two conditions must both hold. First, the relative phase phi must not be 0 or pi. Second, the two frequencies must differ, alpha not equal to beta.
Walk me through why phi has to avoid 0 and pi.
Look at the imaginary part of J23. It's the time average of the sine of A3 over beta omega naught times sine of beta omega naught t plus phi minus A2 over alpha omega naught times sine of alpha omega naught t. Now here's the symmetry trick. Split the integral and in 1/2 substitute t prime equals minus t plus t, a time reflection. When phi is 0 or pi, the driving function has a definite parity under that reflection. The integrand becomes odd, and the two halves cancel exactly. The imaginary part vanishes. So at phi equals 0 or pi, J23 is purely real, no flux.
So phi is the time reversal breaking knob. A generic phase offset destroys the reflection symmetry within a period, and the imaginary part survives.
That's the physics precisely. A finite phi that isn't 0 or pi breaks the time reflection symmetry, which is the microscopic origin of the effective magnetic field. Time reversal symmetry breaking is exactly what a magnetic flux requires.
And the second condition, alpha not equal to beta. Why do the frequencies have to differ?
Also in Appendix C. Suppose alpha equals beta, same frequency, omega equals alpha omega naught equals beta omega naught. Then you can combine the two sine terms. Any sum, a sine x plus b cosine x, can be rewritten as a single sinusoid, capital R sine of x plus gamma, with amplitude r equals the square root of a squared plus b squared, and a phase gamma with tangent gamma equals b over a. When you do that algebra, J23 collapses back to an ordinary Bessel function, J naught of r, which is real. Specifically, r equals 1 over omega naught times the square root of a2 squared plus a3 squared minus 2a2 a3 cosine phi.
So, at equal frequencies, even with a phase offset, the two drives just add up into a single effective sinusoid, and you're back to a plain, real J naught. No complex phase, no flux.
Exactly. You need genuinely different harmonic content, alpha not equal to beta, so the two drives can't be merged into one sinusoid. Then and only then does the generalized Bessel function stay irreducibly complex, and the flux is non-zero. So the recipe for flux is 2 driven sites, 2 different commensurate frequencies, and a relative phase away from 0 and pi. Miss anyone and the flux collapses.
This is exactly the kind of thing that bites you in simulation. If RO3 ever returns zero flux, the first debugging checklist is, did alpha equal beta by accident, or did phi drift to 0 or pi?
That's the correct instinct, and it's worth building as an assertion in the code. Now the beautiful experimental result is that all 3 quantities, the 3 bond magnitudes and the flux, are simultaneously and independently controllable. Figures 9 and 10.
Take me through figure 9 first, the tunneling ratios.
They note that only the ratios of the 3 bonds matter physically, so they parameterize by 2 numbers, x equals j min over j max, and y equals j mid over j max, smallest over largest, and middle over largest. Then they scan the drive amplitudes A2 and A3 and ask, which ratios can I reach? Figure 9 shows they cover the entire allowed region. The lower right unit triangle in the XY plane is completely filled. Every possible ratio of the 3 bonds is achievable.
Full coverage, and they do it for both alpha equals beta equals 1 and alpha equals 1, beta equals 2.
Right. And they note something practically useful. Even at fixed base frequency, many different drive settings give the same tunneling ratios. There's redundancy, which means you have slack to satisfy other constraints simultaneously, like a target flux, which is figure 10.
Figure 10 is the flux control. What's the setup?
They fix a target ratio, J mid over J max equals 0.5, J min over J max equals 0.3, and then ask whether they can sweep the flux through the full range, minus pi to pi, while holding those ratios fixed. They set up a cost function to minimize. F equals x target minus x squared plus y target minus y squared plus 1/20th times phi target minus phi squared. 3 terms, 2 for the ratios, 1 for the flux with a relative weight, minimized over the 3 control parameters A2 over omega naught, A3 over omega naught, and phi.
And the result?
They can drive the cost function below 10 to the minus 10 across the entire flux range, meaning for any desired flux from minus pi to pi, they find drive parameters that hit the target ratios essentially exactly, and the target flux. Figure 10a shows the required A2, A3, and phi as smooth functions of the target flux. 10b shows the 3 bond magnitudes staying in fixed ratio while the flux sweeps. And they stress-tested it over 100 random target ratios, all solvable across the full flux range.
So the triangular plaquette is a fully programmable unit, 3 bond strengths and a magnetic flux, all 4 dialed independently. That is a complete building block for a 2-dimensional lattice gauge theory.
A complete building block, and they're explicit that it's a stepping stone toward a fully programmable 2-dimensional tight-binding model. One more elegant symmetry they note. Sending phi to minus phi flips the sign of the flux. Phi goes to minus phi, while leaving the magnitudes untouched. So the phase offset is a clean time reversal knob. Its sign is the sign of the effective magnetic field.
Let me ask about robustness again, the Floquet gauge business. The flux is computed from the effective Hamiltonian, but the exact object is the T0-dependent stroboscopic one. Does the flux wobble with T0?
They check it, Appendix B, Figure 13. They compute the flux both ways, from the 0th order effective Hamiltonian, which is T0 independent, and from the stroboscopic Hamiltonian, scanned over all starting times T0 in a period. The stroboscopic flux fluctuates around the effective Hamiltonian value, but by less than about 10%. In their example, the wobble is around 1/10 of pi. So the flux is a robust, gauge quasi-invariant quantity with small controllable micro-motion-induced ripple. Good news for us, it means RO3's flux is a real observable, not a gauge artifact.
Now, there's a second route to flux in the paper, section 4c, that doesn't use 2 frequencies at all. It uses static offsets plus a single drive. This is the one that makes the magnetic field gradient. Tell me how that works, because it feels like a different mechanism.
It's the resonant driving route, and it's the classic laser-assisted tunneling idea of Adelsberger, Kettler, and others, now made local. The setup: each site j is driven as wj of t equals a cosine of omega t plus phi j plus nuj times omega. Same amplitude a and frequency omega on every site, but two site-dependent things: a phase phi j and a static energy offset equal to nuj times omega. An integer nuj times the drive frequency.
Static tilt whose steps are quantized in units of the drive frequency. That in units of omega is a resonance condition, isn't it?
It is exactly a resonance. If neighboring sites are offset in energy by a multiple of omega, the drive is resonant with that energy difference and can restore the tunneling that the static tilt would otherwise suppress, photon-assisted tunneling. The atom borrows nu ij quanta of energy from the drive to hop across the tilt, and the restored hopping comes with a phase inherited from the drive phases phi j.
Give me the effective bond.
The renormalization factor becomes epsilon ij equals j sub nu ij of aij over omega times e to the minus I nu ij xi. Let me define the pieces. Nu ij is nu I minus nu j, the difference in the integer offsets across the bond. That becomes the order of the Bessel function. Aij is 2a times sine of phi I minus phi j over 2, an effective amplitude set by the phase difference. And xi ij is phi j plus phi I minus pi over 2, a phase set by the sum of the drive phases.
So now the Bessel order is not zero. It's nu ij, the offset difference, and the whole bond carries an explicit complex phase, e to the minus I, nu ij xi ij.
Right, and that's the crucial difference from the one-dimensional story. There, everything was J0, order 0, and real. Here, along the tilt direction, the offset difference nu ij is a non-zero integer, so you get a Bessel function, J sub 1, or higher, and an explicit phase. That phase, accumulated around a plaquette, is your flux. And the condition to make it non-zero is just that the reflection symmetry is broken. Phi I minus phi j not in the set 0, pi, much milder than the two-frequency scheme.
This is Appendix E. They derive that from the Peierls phase integral.
They do, and it's a satisfying calculation. Start from the lattice frame Peierls phase, phi ij of t equals minus the integral of wj minus wi plus a gauge constant. Plug in the drive with the static offset. You get two pieces, an oscillating piece, minus a over omega times sine of omega t plus phi j minus sine of omega t plus phi I, and a linearly growing piece, nu ij omega t, from the static offset.
The linearly growing in time piece is unusual. Normally Peierls phases oscillate. What does it do inside the time average?
It's the resonance engine. When you time average e to the I phi ij of t, that linear term, e to the I nu ij omega t, multiplies the oscillating exponential. Combine the two sine terms into a single sinusoid of amplitude aij, using the same sum to single sinusoid identity as before, and you're left with the time average of e to the I times a sine times e to the I n omega t. That's precisely the integral representation of the Bessel function of order n. The linear term selects out the nu ijth harmonic, giving j sub nu ij instead of j0, times a leftover phase factor. That's where the complex phase and the higher order Bessel both come from.
Elegant. The static offset promotes the Bessel order from 0 to a nu and drags a phase along with it. Now the application, the magnetic field gradient, figure 11. What are they building?
A two-dimensional square lattice, actually a ladder in the detailed example, where the flux through each plaquette increases linearly as you move along one direction. A flux gradient. That's what a spatially varying magnetic field looks like on a lattice. The flux per plaquette is the local field, so a linear ramp of flux is a constant field gradient.
How do they choose the phases to get a linear flux ramp?
They parameterize the drive phase on each site as phi j equals h times nj plus f sub mj times g. Here nj and mj are the y and x coordinates of the site. H and g are constants, and f sub m is an x-dependent factor. The tunnelings along x are renormalized by j0 of a prime times sin of G over 2 times the magnitude of Fmi minus Fmj, where A prime is 2a over omega. The tunnelings along Y, the rungs, carry the complex phase and are renormalized by a J1 Bessel.
And the trick to get a linear gradient is a specific choice of the FM sequence.
A gorgeous one, Fm is the MTH triangular number, 0, 1, 3, 6, 10, and so on. The running sums 1, 1 plus 2, 1 plus 2 plus 3. Why triangular numbers? Because the flux in a plaquette depends on the difference of consecutive Fm values, and the differences of triangular numbers are the integers 1, 2, 3, 4, a linear sequence. So consecutive plaquettes get fluxes G, 2G, 3G, and so on. A linear flux ramp. Figure 11c shows exactly that, a staircase of linearly increasing plaquette flux across a 20 by 2 ladder extracted from the stroboscopic Hamiltonian.
The discrete derivative of triangular numbers is linear, so their second difference is constant, a constant field gradient. That's a genuinely clever bit of lattice engineering.
And they show its scales. Figure 11e is a 20 by 6 system with a smooth linear flux gradient in the x direction. Meanwhile, the tunneling magnitudes stay nearly uniform, fluctuating by only a few %, because for small a prime, the J0 factors are all close to 1. So you get an inhomogeneous magnetic field on top of a nearly homogeneous hopping lattice. That's a real experimental target, simulating a charged particle in a magnetic field gradient.
Let me steer us to implementation, because our sims are only meaningful if this is buildable. Section 5. What does it actually take in a lab?
The core requirement is local, time-dependent potentials on individual sites. They argue current technology already suffices. The simplest conceptual version uses both blue detuned and red detuned beams, modulated out of phase, to make an on-site energy that oscillates symmetrically around 0. In practice, you'd more likely apply a common offset and modulate around it, needing only one wavelength.
And the hardware to steer the beams.
For moderate system sizes, acousto-optic deflectors, the same technology as tweezer arrays. Each beam is focused on one site and its intensity modulated. Their bandwidth vastly exceeds the required modulation frequencies, which sit around omega between 20 and 100 times J, corresponding to at most a couple hundred kilohertz. For large periodic patterns like long SSH chains, you'd combine acousto-optic modulators for the time modulation with spatial light modulators, digital micro-mirror devices or liquid crystal modulators to paint the spatial amplitude map.
The obvious worry is crosstalk, your beam meant for site B leaking onto site B plus 1. How bad is that?
They address it head-on, and the answer is reassuring. First, quantum gas microscopes already have the numerical aperture to resolve single sites. They cite the Munich microscope at numerical aperture 0.68. If you use a modulation wavelength shorter than the lattice wavelength, 532 nanometers modulation versus roughly 1064 nanometer lattice, the focused spot is tight on the target site. And because the required modulation amplitude is small compared to the lattice depth, typically under 5%, the direct effect on the bare tunneling is minimal, and the low modulation frequencies keep you from exciting atoms to higher bands.
And if your optics aren't that good,
That's the elegant part. The leakage is correctable. If the beam meant for one site spills onto its neighbor, you simply apply a compensating opposite modulation to that neighbor to cancel it. Because, remember the master lesson, only the relative modulation across a bond matters. They show numerically that even with a beam waist, twice the lattice spacing, which is a modest numerical aperture below 0.2, you can perfectly cancel the crosstalk at the cost of only a factor of 4 more laser intensity. That's a very forgiving requirement.
so the whole scheme degrades gracefully. That's the mark of something that'll actually get built. And they contrast it with the alternative, directly modulating the tunneling barrier.
They do, and their scheme wins. Directly changing the barrier between two sites requires focusing light in between sites, with sub-lattice site resolution and stability much harder. Their on-site scheme needs only to address sites, not the gaps between them, and it comes with the bonus of sign control and complex phases, which barrier modulation can't give you. So it's both easier and more powerful.
One thing they flag as the eternal Floquet caveat, heating.
Floquet heating, yes. Every periodically driven interacting system eventually absorbs energy from the drive and heats toward infinite temperature. It's the ultimate practical limit, but they note their scheme's flexibility helps. You can choose modulation frequencies that dodge single-particle multi-photon resonances, the worst heating channels. And there's a tantalizing extension. If the beams are not too far detuned, they produce spin-dependent potentials, so you'd get spin-dependent renormalized tunnelings, opening local control over spin Hamiltonians in the Mott regime. But that's beyond our scope tonight.
Let me pull the whole thing together for our project. If I'm briefing a new engineer joining QuantSim, what are the load-bearing takeaways from this paper?
I'd give 4. First, the master mechanism. Periodic on-site driving renormalizes each bond by a Bessel function, J times J naught of the relative drive amplitude over omega. That single dial weakens, nulls at 2.405, and sign flips the hopping. That's RO1, figure 2C.
The scalpel, number 2.
Second, only relative drive matters, the difference across a bond, which is why you get individual bond control from global-looking drive patterns, why crosstalk is cancelable, and why the SSH sign flip trick works. From that, a period 4 drive builds the SSH model with a protected topological edge state. That's RO2, figure 5.
Number 3.
Third, in 2 dimensions, loop phases become physical, gauge-invariant flux. 2-frequency driving of a plaquette, different commensurate frequencies alpha and beta, and a relative phase phi away from 0 and pi, makes a bond genuinely complex and threads a controllable Aharonov-Bohm flux, the argument of the product of the 3 bond amplitudes through the triangle, independent control of all 3 magnitudes and the flux. That's RO3, figures 9 and 10.
And number 4, the one that keeps us honest.
Fourth, the whole thing is a controlled approximation. The Bessel result is 0th order in 1 over omega. The first-order correction vanishes identically in these on-site driven one-dimensional models. So errors are 1 over omega squared and tiny for omega, a few tens of J. The stroboscopic Hamiltonian is the exact check, and the flux wobbles under the Floquet gauge by only about 10%. So when we later paint a black hole horizon as a spatial profile of Bessel renormalized bonds, we can trust that the atoms feel the effective Hamiltonian we designed, provided we keep omega large and honor the scale separation.
And that last point is the umbilical cord to pillar A, the horizon physics. The companion paper takes exactly these bonds and shapes them into a curved spacetime. This paper is the proof that the shaping tool exists, is precise, and is buildable.
That's the right framing. Nixon, Unal, and Schneider hand you a fully programmable one-dimensional hopping chain and a flux-carrying 2-dimensional plaquette, out of nothing but shaking on-site energies with tweezer-grade optics. For an analog gravity simulator, that's the whole workshop, the lathe, the drill, and the vise. Everything we build on the horizon side is cut with these tools.
Before we close, let me test one thing I want to be sure I understand. The generalized 2-variable Bessel function for J23. Is there any closed form we should use in the sim, or is it numerics all the way?
For the general case, alpha not equal to beta with a phase, it's numerics. You just evaluate that time integral directly, which is cheap. The paper is candid that the multi-frequency expressions resist clean analytics, but they're trivial to integrate numerically and to optimize over. Only in the degenerate alpha equals beta case does it collapse to a single ordinary J naught of that R I gave you, the square root of A2 squared plus A3 squared minus 2, A2 A3 cosine phi over omega naught. So in RO3, evaluate the integral numerically for the flux and use the closed form only as a sanity check in the equal frequency limit where flux must vanish.
That's a clean test to build in. Equal frequencies must give 0 flux, and the closed form J0 must match the numerical integral there. If it doesn't, something's wrong upstream.
Exactly the kind of internal consistency check that keeps a simulation honest. And it echoes the paper's own discipline. Every analytic claim cross-checked against the numerically exact stroboscopic Hamiltonian.
Last question. If someone only remembers one number from this entire episode, what should it be?
2.405. The first zero of the Bessel function J0. That's the drive strength, A over omega, at which a bond vanishes, where the lattice, in effect, tears. Every disconnection, every horizon edge, every severed link in our simulations lives at or is measured against that number. Weaken toward it, null at it, sign flip past it. If you internalize that single curve, J0 of A over omega, you understand this paper.
2.405, the tear in the lattice. George, this was exactly the deep math-forward pass I wanted. Thank you. That's Nixon, Unal and Schneider, local periodic driving for individually tunable tunneling, and it's the Floquet toolbox our whole black hole simulator is built on.
My pleasure. Go reproduce those figures, R01, R02, R03. And when the Bessel curve falls out of your stroboscopic Hamiltonian right on top of the analytic line, you'll know the toolbox is real in your hands, not just on the page.